All right, we're still in Unit 1. We're still in Chapter 5. We're just cycling back around, spiraling back around here in AP Stat, talking again about percentile ranking, just as a refresher to see where we're at. Again, percentile rank is also useful when the exact population size is not known. All right, so if I don't know how many people took the SAT, it doesn't matter. All right, it's also useful just to see what percentage of the people you're better than, right? So for example, it is more meaningful to say that Jennifer scored in the 90th percentile on a national exam rather than trying to determine her exact ranking among some large numbers of some test takers. Instead of saying that you were, 118,000 out of 4,847 people, it's easier just to say an exact percentage. And this means that you are better than 90% of the people who took it. With percentile ranking, again, quartiles are basically percentiles. You have quartile 1 and 3, and they lie on the quarters, right? That would be the 25 percentile, and that would be the 75th percentile if we were looking at it, right? That's all that those are, respectively, because they cut your box and whisker plots, if you remember, your quartiles into quarters, literally. The interquartile range, we went over this now a couple times again, spiraling through. We defined it earlier. It's between basically the distance between the first and third quartile. We also have deciles, which lie 1/10, all right, 9/10 away up a list, respectively. So you have percentiles, but they could also have deciles, which are basically, instead of quartiles, which are quarters, this is breaking it up into tens the whole way, right? So a list, respectively, we have percentiles as 10% or the 10th, and the 9th% or the 90th, right? Same idea with those. We also went over z-score already. Z-score is a measure of position that takes into account both the center and the dispersion of the distribution to figure out how far away it is, and kind of classifies again all the data so we can compare it much easier. Different units, different measurements, it doesn't matter. We can put it all into the same look with a z-score. And the z-score of value tells how many standard deviations the value is from the mean, which is what also makes it very crucial and neat here. Mathematically, again, you find whatever you're looking for minus the mean, and that gives a raw distance between the two. All right, and then we divide it by the standard deviation. That's the population mean. That's the population standard deviation. Converts this into a number for us, right? And that's that formula right there, where x, again, is the raw score, whatever you're looking at. Mu is the population mean, and the sigma there, that is the population standard deviation. This is the same exact formula. That's what you're looking at, that raw score. That is the sample mean and the sample standard deviation. But it's the same formula for the most part. Same way of finding the z-score for the most part. Again, just wanted to elaborate and make sure you are aware. And if the z-score is greater than the mean, right, then the z-score will be positive, right? If the z-score is less than the mean, then it'll be negative. And you can have a negative z-score. It's just telling you the placement along the line is all. And if we are given the z-score, we can then find the raw score by basically reversing everything in the procedure. We could figure out, if we know the z-score and we know the mean and we know the standard deviation, we can find out what we initially were given. So this is just me showing you, hey, if I multiply both sides by sigma or standard deviation on both sides, it would become this. I could easily find x. I just flipped it around for you. Take the z-score times your standard deviation and basically add your mean to it, and you're good. So here's an example. In 2012, because of hurricanes, refinery outages, and Middle East tensions, the average mean of gas in New England City was $3.80 per gallon with a standard deviation of 5 cents. Okay, so in a New England city, that's what you're looking at. So then 390 has a z-score of, so basically put the 390 in, that is our mean, that is our standard deviation. So boom, boom, right on the button, 2. All right, you plug it in, we solve it, it's 2. Again, if I'm moving too fast, that's fine. All you need to do, if I'm moving too fast, is to pause the video and copy some of this stuff down. Now, while $3.65 has a z-score, if I was to look at that now, let's say we found that one. Put that in. That was our mean, and that was our standard deviation before. That's -3 standard deviation. So point being is, if you remember, if you're within 2 standard deviations plus or minus of the mean, that's basically telling you that it's a usual thing. This is hanging out there. This $3.65, that's unusual is what they're saying. All right. Alternatively, if I found a z-score, if I knew the z-score was 2.2, I could figure out what the raw score was, because I could plug the 2.2 in here. I know what the mean is, 380. I know what the standard deviation is 0.05. I could basically solve it. That's all I'd have to do to see what z equals, right? So that's what I'm doing down here. Basically what I'm saying is, hey, I want to figure out what it is. I know what the mean is, right? I know what the mean is. I know what the z-score is. I know what the standard deviation is. I can plug it all in, and I get $3.91. It's basically what that is, right? And alternatively, a z-score of negative 1.6, if I know the z-score and I know the standard deviation is 0.05 and I know the mean is 3.8, right? Plug all that in, and I get roughly $3.72, okay? Sometimes it's useful to portray integer z-scores and the corresponding raw scores as it follows. So just so you can see both and compare them and say, here's the mean at 0, which is what you're going to find out when we rewrite everything in terms of something that is a normal for us, a normal distribution, and we start using our z-scores. It creates a template that it doesn't matter what these are, this is a corresponding z-score to each individual item, and in turn we start rewriting everything in terms of z-scores. We basically can alter whatever data we're given to put it into z-scores in a table. It'll help us use our calculators eventually down the road to find some of these answers, with the mean being 0. Okay. Here's another example. The world's largest cinema complex is in Madrid, Spain, and has one screen with attendance averaging 780 with a standard deviation of 40, right? So adding multiples of 40 to the subtracting multiples of 40 from the mean of 780 gives. So if we are adding multiples of 40 and subtracting multiples of 40 to the mean of 780 gives us, right here is 780, adding multiples of 40, subtracting multiples of 40, that's what it gives us. That is the actual number of people, is basically what that's getting at, and here is each standard deviation that matches it. That's all. That's the theater attendance versus the z-score is all that we're saying. Theater attendance of 835 is converted to a z-score as follows. So it's not going to land right on the button. As you can see, 835 is not on here. Somewhere in between here, but it's not exactly on here. So what they're saying is, we could find out exactly where that is and where it's located, because I could put the 835 in here. I know what the mean is, that's 780. I know the standard deviation is 40. So I end up finding 1.375 as my z-score for this. A z-score of negative 2.15 is converted to a theater as well, because I could basically say, well, I know the z-score is negative 2.15. I know the mean is 780 and the standard deviation is 40. I could multiply by 40 and add 780 over to get my answer, or just plug it in here. And I would figure out that that's roughly 694 people that are in attendance at negative 2.15. So what I did here was I just showed you, hey, look, that is where 835 is, and that's roughly where 1.375 is. Here is where the 694 is roughly, and this is where the corresponding z-score is to it, just so you can see in comparison. They still match, okay? We also hit on the empirical rule, right? Before, we'll spiral back to that. The empirical rule is also called the 68-95-99.7 rule. It applies specifically to the symmetric bell curve for data that you're used to seeing. This idea that we're talking about of the empirical rule is great. It does not work with skewed data at all, right? Skewed left or skewed right. In this case, about 68% of the values lie within one standard deviation of the mean, right? 68% lie within one standard deviation of the mean, and this should now be review. That's why I'm spiraling back through this. 95% of the values lie within two standard deviations, right? 99.7% of the values lie within three standard deviations of the mean. And basically, this is how it looks split up using the empirical rule. If you were to take still 68, if you add all that up, it's still 95, 99.7 with all three of them, and it's with each section, with the empirical rule. So again, if I take a look at another example, it says, suppose that taxi cabs in New York City are driven an average of 75,000 miles per year with a standard deviation of 12,000 miles. All right. What information does the empirical rule give us? Well, let's look at it visually, right? There's 75,000, 12,000 up, 12,000 up, 12,000 up, right? Or 12,000 down, 12,000 down, 12,000 down. So it says, here is what this visual tells us. Back here it says, when we're looking at all this, right, what information does the empirical rule give us? All right, take a look at something like this now. All right, I can see what each section is. Now that I have a visual aid, I can see what's going on. All right, using the empirical rule. All right, we can see that approximately 68% of the taxis are driven between 63 and 87,000 miles, right? Between here and here, 68% of all taxis are driven. 95% of all taxis are driven between 51,000 and 99,000 miles. That is 95%. That's within two standard deviations. That is something that is usual. But anything above 99,000 miles is an unusual measurement. And anything below 51,000, that is also an unusual measurement when talking about driving. Basically is what we're saying. And we can see that approximately 95% of the taxis, again, are between 51 and 99,000 miles. We can see that approximately 99.7% of the taxis are driven between 39,000 and 111,000. So anything outside of that is extremely rare and extremely unusual if that was to occur. The empirical rule also gives us useful, quick estimates of standard deviations in terms of the range. And we can see, using the prior picture, that 95% of the data falls between 4 standard deviations, or between -2 and 2 of the z-score. 4 total, 2 on each side. 99.7% of all data falls within 6 standard deviations total, or -3 to 3 on each side. We can also use the empirical rule to quickly point out gross arithmetic errors, since we can quickly estimate the percentages. It's basically what the empirical rule is helping out with. We can see if our quick judgment, how far off maybe it possibly is, by just quickly setting up a table using the empirical rule and trying to figure it out. Okay. We'll stop right there. And when we come back, we'll continue on with some more of the empirical rule and spiral back through some more, and hopefully try to finish up these notes on Chapter 5 in Unit 1.